Okay, right. Some fun questions regarding friction before we move on to the real portion. Now, imagine you're in a car and you're moving this way. Suddenly you see someone in front of you. So obviously you brake, right? Obviously you brake, right? Unless it's someone you really don't like, and then you accelerate. Okay, so you brake and therefore the friction you slow down. Now, is the car going to be like this when you brake? Or is it going to be like this when you brake? Or is it going to be like this when you brake? A, B, C. When you jam brake as the car is moving towards the right, is the car going to settle into position A, position B, position C? In case you have spatial issues, in case what's the difference? Then I'm really worried. This is flat, this is like this is like this. B, right? From your experience. My question is, why? Why? We all experienced this before. You're in the bus is going this way, it jams brake, then you just like shift your leg towards here. So you tend to move towards the direction of velocity. Why? Do you still remember this really nice topic in year 3 that you've done before that starts with a letter M? Moments, exactly. Motion moments, yeah. So let's take a look at moments. Is moment a vector or scalar? Is it a vector or scalar? Vector or scalar? Then the question you should ask yourself is, does direction matters? It does, right? So it is a vector. But you take distance multiplied by force. So why is it that it's a vector? Why distance? Clockwise. But how do you take one vector times a scalar, then it becomes a vector? A scalar times a vector, basic math, it will always result in a longer vector. Right, scalar. But now then you have two vectors multiplied together, distance and vector. Then how does it work out to be a vector? So, have you learned vector product yet? Have you learned cross product, dot product? Okay, you haven't. Looking at the face, or I don't know whether it's after lunch, comma, or but vector product means that it's a product of two vectors. It can result in either a scalar or vector. Okay, let's come back to this. Moment is a vector in short. Okay, moment is a vector. Now, do you agree that the frictional force over here, F1, F2, and there is a N1 and there's a N2 over here? All the forces acting. And now, of course, obviously, you've got a weight here. Now, if you take moments about here, can you tell me how many clockwise moments there are? How many clockwise moments are there? About the center of gravity. How many? 3? Yeah, so F1, F2, and N1, exactly. And N2 is the only one that produces the anti-clockwise moment. So there is a very strong tendency for the vehicle to turn clockwise or anti-clockwise. Exactly. And that's why it goes into this position. Can? Yeah. You haven't done circular motion yet, but just imagine a vehicle that is going round a circle where the center of gravity, the center of the motion is here. So the car is going forward and turning right. Now, do you agree that the normal contact forces is going to be N1, N2, about here, and you've got frictional forces supporting the circular motion? That means the friction on the floor is holding the car, preventing it from going this way, as it is making it around this way. Now, if you take a look, this one, and this one, they all causes the car to go this way. Whereas this force over here causes the car to go this way. So if the car were to go too fast, where do you think the car will flip? Towards the right or towards the left? Where do you think is the tendency for the car to flip? Towards the left, towards the right? I hope you never have this kind of experience though. Real life experience. So I just experienced it yesterday. My car flipped. No. I'm just saying, for example. Relax, Anna. My car didn't flip. Choi! Which one? Will it flip towards the left or will it flip towards the right? It will flip towards the left. Yes, correct. So when the car goes too fast around, it will tend to flip away from the center. Why? Because of three forces creating moments here. Whereas there's only one moment creating over here. Okay. Which one is the? So in which direction is the car? Oh, the car is going forward into the board and turning right. That means this is the center of the circle. Ken? Yeah, this is the center of the circle. Go straight and turn right. Now, in the next few topics, we're going to talk about why is there a force required and all these things. Okay? But to come back to this point, you don't need to know moment about for IB syllabus, but I feel that that's shortchanging you because moment is such an important thing in real life. I'm surprised, honestly, why IB doesn't include moments, but I feel that we need to know moments to understand and appreciate certain things that happen in real life. Cool? Ken? So let's go back to important things that you need to know regarding frictional forces. Now, can someone tell me if an object is on the ram, how many forces act on the body? And what's the name of each of them? No trick question now, relax. This one, wait, confirm right on. Normal contact force, upwards? Yes. If it is not moving, it's frictional force, right? Okay, good. Before I go into the dynamics of these three forces, can someone tell me what's the origin of normal contact force? We know that gravitational force is because of the attraction between two masses, and of course Einstein said there's a space-time warp. What is the origin of normal contact force? Yes, that's the relationship between the two forces. But what if you open up, go very deep down? What is the origin of normal contact force? What gives rise to normal contact force? The repulsion of the electron, correct. The reason why you're sitting on your chair right now is because of electrons on this portion repelling with the electrons on the chair. So the reason why you don't fall right through is because of electronic repulsion. So you need to appreciate at that level. It's electron. The reason why you can walk and not zoom is because of repulsion force, electrostatic repulsive force. Ken? So build this habit now. Whenever you look at what's the nature of this. Ken? Okay, so these three forces, can I challenge you to draw these three forces in a vector diagram? And then showing how these three forces adds up to give you zero force. Let's try that first. Let's see whether you know how to draw a vector triangle. Since it is in equilibrium, got something like this. The three forces must form a closed loop, and it must be pointing in the same direction. Okay? Just a quick check, everyone okay? This is the diagram you should have. Now let's push a little bit further. Can you see that if I were to resolve the weight, there are two components of weight, W parallel and W perpendicular, and this is theta. Now, do you agree that frictional force has to be equal to W parallel? Ken? Now, W parallel, did I go through this the last lesson that is mg sine theta? Did I go through this? Yes or no? Okay, from the look on your faces, some of you say no. Okay, no worries. Let me show you. If I were to resolve this and this is weight perpendicular, this is weight parallel, this is theta, this is 90. What is this? 90 minus theta, and therefore this is theta, right? And therefore W parallel over W must be equals to sine theta, and that's why W parallel is equals to mg sine theta. Follow? Now this force you can quote without deriving. In exams, you can just say that W parallel equals to mg sine theta. There's no need for you to derive. You can quote. You won't be penalized. And make a guess, what is W perpendicular? Excellent. Now allow me to be a devil advocate and then explain, ask you, why can't you resolve the force this way? Why can't you resolve weight into like this, then W parallel would be equals to W divided by sine theta. Yeah, I think you kind of say the right phrase. Exactly. You see, what's the consequence of this if this is correct? It means that W parallel is equals to mg upon sine theta, which is equals to ma. Say, for example, if there's no frictional force, you divide this, a is equals to g sine theta, which means the object will slide down faster than g. That's not what you observe. Agree? So, remember this very important rule that whatever you resolve, which is this one, it must be the hypotenuse, correct? Must remember this. Whenever you resolve something, it must be the hypotenuse. Okay? So what's the consequence of this? Now let's take a look. Remember f equals to mu n, therefore mg sine theta is equals to mu mg cos theta. And you strike this off, mu is equals to tangent theta. Now, some of you, you're going to do IA on frictional force. Like how does the temperature of a surface affects the coefficient of friction? Some of you will investigate, say for example, how will the roughness of a surface affects the coefficient of friction. So how do you find out what's the coefficient of friction? Very simple. You put something on a ram, say for example the coefficient of friction of my wallet on this thing. How do I know what's the coefficient of friction? Very simple. You just need to raise it until it starts to slide. Then you calculate angle theta, tangent theta. That's your mu. Neat, right? You just need to do this. Hold it there, measure angle theta, tangent theta, that's your mu. It's a very neat way of finding mu. Okay? But you must remember, it is only when the thing starts to slide down, that's when you take the value of the theta. Anyone can tell me why? Why only when it starts to slide down, then you measure the theta? Because mu n is the maximum frictional force. Yes. Because beyond that, the frictional force can no longer be equals to mg sine theta. And that's why it will slide. Cool? Are you still alive? Now, to push your ability to resolve forces a little bit further, let's see whether you can do this. Theta over here, m over here, this is mu. Find the limits of f so that object can remain on the surface. I have a force that's exerted horizontally, and there is a limit, a maximum and a minimum value, so that the object will actually stay on the surface without moving. What is interesting about this question is that there is actually a range. Most of the questions that you solve in O-levels or in your exam papers, it is one value, right? Most of the time it's one value, but this has a range. Why so? Why so? This is a very important step in understanding questions and solving questions. What is happening? What exactly is happening? So why is it that there is a range? Think about this. If f gets too small, what happens? If f gets too big, what happens? If f gets too small, where do you think the object will slide? Down, correct. If f gets too big, where do you think the object will slide? Up, exactly. So you need to write two different equations for the two scenarios. The frictional forces are opposite direction. Be very careful, huh? The frictional forces are opposite directions. Write two equations, get the two values for forces, the two expressions for forces, and that will be your maximum and minimum. Give it a try. Give it a try. And be very careful on the force. There are two components, one F perpendicular and one F parallel. Give it a shot. Oh, the posters have been rearranged. Anyone rearrange it? Okay. My goodness, whose marker bag is this? Any idea? Probably belong to Marcus. Huh. Okay, that's just stupid. Okay, sliding down. How do you test whether your equations are correct? Tell me. In exams, if you were to get two expressions, how do you know whether the expression is correct? Or how do you know that it may be correct? Yeah, Lily?
I'll say that I'll be lucky enough to get an expression.
It's like, I can write equal means. I don't know, just write F equals MA. Yeah. Just hammer F equals MA. At least it looks intellectual. F equals MA. Now, what on earth is happening here? Okay, let me explain this one so that hopefully you can make sense out of this one. Yeah? So if it is sliding down, what's the direction of friction? Down or up? Up, yes, correct. So therefore, this is mg sine theta. This is frictional force. This is your F cos theta. Why F cos theta? Because remember, when you resolve, the force that you resolve has to be the hypotenuse. So if this is theta, this is theta 90 minus theta, and actually straight away this is theta. So if this is force, this will be F cos theta. Therefore, this plus this must be equal to this. Or you can see the other way around, if F plus F cos theta equals to mg sine theta. So that's why mg sine theta minus F cos theta equals to the friction. And the friction, the normal contact force, you have to include this component due to F as well. Okay? So if you throw everything in, you'll be able to get an expression for F. One of the ways that can check whether the sliding up and sliding down may be correct is to set mu to be equals to? Set mu equals to? How should these two expressions compare if mu equals to 0? On a perfectly smooth surface, how should this compare with this? Same, correct. Check whether it's the same. Yeah, if it is different, it means confirm stem job wrong already. Yeah, if it is the same, probably at least correct. Yeah, probably is correct. And if you look at the sliding up case, there's a very interesting scenario. Why is there f sine theta? Okay, because you resolve, okay, probably for the convenience of your side, if you have an f over here, this will be your f sine theta. So the additional normal contact force that it exerts over and above mg cos theta, it actually pushes the object into the ramp. That's the additional the normal contact force. And it's the same regardless of whether it is going to slide up or slide down. Okay? This is a little bit of math. Whenever you do physics, right, you need to be sensitive to maximum point, minimum point, zero, and infinity. These few things. They are very interesting points. Maximum, minimum, zero, and infinity. Now take a look at the expression on the right. Is there something interesting about the expression on the right? When mu takes a specific value, something goes haywire. When mu takes a specific value, look at this. Can you see that when mu equals to cotangent theta, what happens? Tsikababooms, right? Tsikababooms. So what does it mean by tsikababooms? What does it mean when it goes to infinity? It means that it's impossible for it to slide up. Yeah, when mu is that value, it is impossible no matter how much you apply. It cannot slide up. Yeah, which is actually quite interesting. When you set mu to be equals to cotangent theta. So there is a case where you cannot slide up. But is it possible for an object not to be able to slide down? Can you create a surface where it is impossible for the object not to slide down? Sorry? Yeah, exactly. So it's not possible. So it is not possible for this case, but it is possible for this case. Can? Yeah. Now the reason why it is not possible for you to slide up is because as you increase F, can you see that you're also increasing normal contact force? Yeah, so you're actually increasing friction as well. So if it is at a certain angle, it just cannot, the upward force cannot surpass the frictional force at that condition. I'm not sure what's the application, but probably in certain cases, it might be interesting to know this. Can? So much about frictional force. I think it's time for us to have a driving force. To focus on driving force. It's a little bit resistive. Talking so much about resistive forces. Any final questions that you want to ask before we start to gain momentum? Before we start to gain momentum. Any final questions about frictional forces? Anything? But remember interesting things that I talked to you about, that you may think that frictional force doesn't depend on the surface area. It actually does. Think about this. Why is it the surface area matters? Why is it that when you have a certain weight and distributed over, say, a piece of rubber, if it is a small rubber versus a big piece of rubber, why does the friction change? Like you put something, a small piece of rubber versus a big piece of rubber. Say the total weight of this system is the same. Somehow, you vary the mass of X such that the total weight of this system is the same. Why is it that frictional force actually depends on area when it shouldn't depend on area? Why is it that frictional force depends on time when it shouldn't depend on time? It's potential IA topics. Think about this. Yeah? These are very novel things that will give the reader, that will give the examiner this kind of, interesting to read. Those of you who want to do physics EE, these are the things that you should go into. Yeah? One student even realized that when you have a plate and we place something on it, when you increase the when you increase the frequency of vibration, it actually changes the frictional force. The faster you vibrate the plate, the lesser the frictional force. And it plateaus at some point, which is actually quite interesting. That you shake a plate, the frictional force has to reduce. Why? Why do you think the frictional force reduces? You are effectively reducing normal contact force. Can you see? When you have something like this, and then you start to do this, do you agree that the normal contact force is reduced? The average normal contact force, yeah. So the average normal contact force reduces, so the frictional force reduces, which is actually quite interesting if you think about this. So there are a lot of things that, by right, it should be like this, but sometimes under certain conditions, it is not like this. If you want to do physics E, look out for those conditions. It might be interesting to go into. Okay? Cool? Okay. Any problems, issues? Okay, today we are still down to earth. We haven't gone to the cosmos yet. Okay. Can someone tell me what's the relationship between F, M, and A? F equals to, and no, relax, no tricks. No tricks, no tricks. Is he up to no good? What's the relationship? Okay. Now, I'm going to show to you that it is incomplete. It's not wrong. I choose the word incomplete. I didn't say wrong. Yeah. Okay. So you learned it before? Yeah, correct. But why so? Let's quote a scenario so they can see, oh yeah, it's actually true. Yeah. Oh, you did it last year?
No.
Oh, you saw it in some books.
Like this senior came in and said, hey guys, you all know that F equals MA.
Ah, right. Yes, it is wrong. And a very classic, interesting model is this one, the sand thing, which I guess you've seen it before. Yeah? So if you drop sand onto this and then it's moving at V constant, for those of you who have never seen this example before, just follow me carefully and you see that F equals MA is not complete. And I'll show you why is it so. So if you have V constant and then the sand comes onto here, do you agree that F equals to MA tells us that this should be equals to 0 because V is constant over here, A should be 0. Correct or not? But we know that if you drop sand onto a belt for V to be constant, obviously you've got to drag the belt along. If you don't have the force over there, what will happen to the belt? You'll stop, you'll slow down eventually, right? So in order for it to continue moving at a constant velocity, there must be a force. So how do you reconcile F is not equals to 0 and F equals to 0? Do you see the contradiction over here? By one route, you say F equals to 0. By the other route, you say F is not equals to 0. So how? Newton's second law is not F equals to MAR. Newton's second law says that F is dP dt. Now in words, it says that net force is directly proportional to the rate of change of momentum. And what is momentum? It is defined as mass times velocity. So can you tell me whether is it a vector quantity or is it a scalar quantity? Is it a vector quantity or scalar quantity? Vector quantity, yeah, because it's a scalar multiplied by a vector, therefore it is definitely a vector quantity. And therefore, F equals to dP dt is equals to dmv dt. Now, how does this land up in F equals to ma? Let's take a look. Do you still remember partial differentiation? Still remember partial differentiation? You keep one constant, differentiate the other one, keep the other one constant, differentiate the other one. Yeah? Yeah, correct. The other way of saying this. Plus v dm dt. So F is equals to ma plus v dm dt. Now someone just now mentioned that if mass is constant, this goes to 0 if mass is constant, and that's why it's equals to ma. Only if mass is constant. And for the secondary school level, you have been always dealing with scenarios where the mass is constant. Now let's take a look at this belt over here. Is the mass of the belt constant? No, it is constantly changing. And therefore, if you take v dm dt, you take the rate of change of mass of the belt, multiply the velocity is moving, you'll get your F. For the belt, MA is 0, but V dm dt is not 0. Get it?
Wait, sorry.
Yep.
Net force is equals or directly proportional to it?
Interesting. Very sensitive to this. You're absolutely correct. If you actually look at the original expression, it is Newton wrote directly proportional. But eventually people set the constant to be 1. Yeah, correct. So the full form, full glory, they're very nice of you to pick this up. The full form is directly proportional. But when we write it as equal because they define it to be 1. Can? Okay. Do you know how powerful this equation is? You know how powerful this is? This is responsible for almost anything that's happening around. The force on the electron that's moving the circuits now. The buses, the cosmos, the neutron stars, everything is responsible for anything that is force. There are 3 fundamental, did I mention 3 fundamental things in physics that makes physics? And that makes chemistry rely on physics. Oh man, recorded! Come on, let's face this lah, yeah? Bio talks about chemical reactions, therefore it hinges on chemistry. Chemistry talks about electronic transfer, which depends on... No. It's not better or not as good. Must be very clear. It's the order of existence. Order of existence, just to be more diplomatic. Okay, so the electron exchanges and everything depends on this thing called quantum physics. Quantum physics, yes, correct. Quantum physics, correct. But there's only one area, one discipline of knowledge where physics have to bow to math, correct? Math is the language of the universe. At this level, we can actually understand the physics concept, then do the math, right? At the very high level of physics, you solve equations, solve, then you try to make sense out of it. Yeah. So you solve, oh, the universe has 11 dimensions. How does it look like? Then you start to understand why got 11 dimensions. Yes, by the way, it's not BS. There are 11 dimensions. Yeah.
Like string theory.
Okay, entertain me. I must remind myself 1 minute later, I must come back to planet Earth. You look at a wire that's very far away from ACS. Say, for example, a wire that's very far away. How many dimensions do you see? 1, right? It's a line. Correct or not? If you go closer, you start to see that the wire has thickness. You start to see 2 dimensions. If you go even closer to the wire, you start to see that it has not only area, but it has volume. That's correct. So it has 3 dimensions. So why is it that we cannot see 11 dimensions? Because we are at a scale that is too big, we cannot see. So if you go smaller and smaller, start to see more and more dimensions. Yeah, mathematically there are 11 dimensions, string theory. All of us are actually vibrating strings. That's quite sad. But hi, I'm string A, you are string B, let's get married. Let's tie a knot. Well, new meaning to tie a knot. Let's tie a knot. Oh. My. So that's what they meant. So actually people in the past, they know string theory. Literally tying a knot. Yep, so it's interesting, string theories. Go and read out on it. Then after string theory, there's a super string. So, okay, let's not get some of this too stressed out. Let's come back to planet Earth. Yeah, let's come to planet Earth. Dream on. We're going to finish syllabus. So, F equals to MA. So, there are 3 parts to the equation. I'm going to do F equals to MA first. I'm going to show you how simple and not so simple it is. I'm going to show you F equals to dP dt, and I'm going to show you F equals to V dF dt. So they're all the same thing, it's just that I'm going to go through them in different scenarios. And you're going to see how interesting the different scenarios are. Okay, F equals to MA, all of us think that we know. Let's see. So if you have this, and this, F equals to 16 Newton. I'm going to start off with something friendly, and then I'm going to go to things which are more interesting. 5 kg, 15 kg, and then we got frictional force, which is 5 newtons and F equals to 15 newtons. Draw free body diagram of A and B. And then find the acceleration and the tension in between A and B. Give it a try. I'd like you to do the free body diagram of A and B first. Give it a shot. Okay, that's a good point. Strictly speaking, if the question just asks you to draw free body diagram, you should include the vertical forces as well, just to be safe. Just to be safe. A good hint for you is to look at how many marks they give. If they give you 3 to 4 marks, everything in. Yeah, if it is 1 to 2 marks, probably no need. Like what I said, just to play safe, everything in. Ken, do you have something like this? Can you tell me what's wrong with the diagram? Wait a minute. I thought that's what I drew. There's something wrong with it. One thing that is wrong. In a free body diagram, the length of the arrow represents the magnitude. So can you, in view of that, can you tell me what's wrong with the diagram? Something is too short or something is too long? The F is too short. Yes, correct. Why? Why is it that it is not the same as this? Where would the whole object accelerate? Towards the right, right? Therefore, do you agree that this force must be bigger than these two combined? Make sense? Because it accelerates. So the net force must be towards the right. Likewise, for example, this one, it must be towards here. And it must be longer than small f. Now, the beauty of F equals to ma is this. You can apply F equals to ma to each of the body here. F equals to ma on this, F equals to ma on this. So let's take a look. T minus F is equals to ma. MAA. And this one, F minus T minus F equals to MBA. How many unknowns do you have? 2 unknowns. How many equations do you have? 2 equations. And you can solve the question. Yep, can. But there is a faster way to find A. I'll show you later. I want you to go through the difficult way first. Then you appreciate the faster way.
Can you just say like the overall like mass?
Exactly. Yeah, exactly. So if you take the overall mass, you'll be able to find A straight away, but you can't find T. You still need to talk about this or this to find T. Because you lose the resolution of the 2 forces. The 2 tangent will cancel. So you need to either use this or this to find T. Okay? Which is a good point. Whenever you want to find A, you always consider the whole system as one body. It's one of the fastest ways to find A. Good point. Okay? So can someone just... I give you very nice numbers. 40. A equals to? 2, exactly. A equals to 2 meters per second square, and tangent equals to? 10. 15? Yep. Good. Excellent. Excellent. Horizontal is always the easy one. When things go vertical, that's when... Oh, no, actually not true. Let me give you a scenario, a horizontal one. Then you see how interesting horizontal questions can be. It's like, what's that? All surface, the interesting thing is the frictional force. You'll see later. All surface has friction equals to 10 newtons. Find acceleration and tension. It's supposed to be a pivot. It's supposed to be a pulley. Yeah, it's supposed to be a pulley. So those of you who are trying this, continue. Those of you who have finished this, got the answers 2 and 15, go ahead and try this. It's a slightly more complicated situation. Be very careful of the direction of friction. Be very careful of the direction of friction. It's like, how does it rub? How does it rub? Yeah, how does it rub? Anyone has issues with the one on the left? I'll just walk around and see whether if you're okay, whether you're able to overcome that friction. Only one person got it. That's okay, no. Okay, yeah, sandwich between two people with IQ, yep, 150 kind, should be fine. Osmosis into your mind. Diffused. Anyone? Everyone okay with the one on the left? I don't want to give you the answer for the one on the right yet, otherwise you'll start reverse engineering. You might want to start off by doing the free body diagram for the 5 kg and the 15. You might want to start off with that first. The interesting part about this whole thing is the frictional force. To improve clarity, let's ignore all vertical forces, shall we? Let's ignore all vertical forces because it's not going to move vertically. Yeah, so let's focus on the horizontal forces so that we add clarity. How many horizontal forces acts on 5 kg? 1, 2, or 3? 2? Yep, there are 2, correct. So one is the tension, the other one is the friction. Pay close attention to where I draw the frictional force. I drew it at the place where the friction acts. I don't draw it anywhere else. Yeah, that's also good free body diagram. How many horizontal forces acts on the 15 kg object? It's like, oh. So there's tension, there's friction. Okay, so this is tension, obviously. Tension pull. Tension never push, in case you wonder. Tension never push. You never tie a string around someone and then push the person. You never. Yeah? There is a F. Obviously friction here, and then friction here, right? Oh no. See. Hola. Same. Correct or not? Anyone want to speak up? You must remember what Terence you write on the board may not always be correct. Sometimes it's intentionally wrong. 1% of the time it is actually wrong. 99% of the time it is intentionally wrong if it is wrong. So, How many of you agree that this should be the free body diagram for the 15 kg mass? Okay, 1, 2, 3. Okay, good. We've got some daring souls. Okay, some people don't know whether they're raising their hands or whether their hands are just preaching. Okay, you got a lot more now. Okay, about half the class. How many of you disagree that this is the free body diagram? How many of you are lost? Okay. If you're lost, I guess that you're not totally lost. You do know that this is correct, right? So the question is, I think this one also not a problem, right? It's this one. Now, the frictional force, this force over here, this circled frictional force, is the frictional force that the 15 kg mass acts on the 5 kg mass. So what's the direction of the force that the 5 kg mass acts on the 15 kg mass? Towards the left or towards the right? Yes, correct. They are equal and opposite. So, over there. Yeah. Can? It might be easier if you imagine it this way. Let's imagine now. Sometimes you need to think of another context, simplify the scenario, then you'll start to understand better. Imagine this one. Let's take away the pulley. Let's take away everything else. Let's consider this. Where do you think is the force that A acts on B? If I were to pull on A is just resting on B. Where do you think is the force by A on B? Towards the left or right? On B, on B. Right. How do you know that it's towards the right? Let's simplify even further. Frictionless surface. Only here got friction. How do you know that the force by A on B is towards here? Think. Where is the direction of acceleration of B? Towards the right. What's the only horizontal force acting on B? Must be towards the right. Therefore, I know that the force by A on B should be towards the right. Can? So I'm showing you a technique. How do you understand a scenario by simplifying it? Remove certain things. How does it behave? Can? This is a technique that you can use. Simplify questions. Think about why and how does it behave if you simplify everything. So therefore, the frictional force by this on this is towards there. It's a little bit counterintuitive because the thing moves here and then how come it moves here? But if you think about this scenario, it makes absolute sense. Okay? So with this, you should be able to find that the acceleration is, drums roll, Shanine? 2.5 exactly. You got to look there. I got this 2 hours ago already. And the tension is equals to? Yeah, 22.5, correct. 22.5. This is 22.5 and this is 2.5. Excellent. Sorry? Can? Anyone like to ask a question on this or this? This is different from your O-level stuff or your secondary stuff because the main difference is in O-levels or secondary stuff, you only deal with one body. In A-levels and beyond, you deal with 2 or 3 bodies. And I'm going to show you when the time comes, I can actually give you infinite number of bodies. I'll show you a scenario. Infinite number of bodies. Okay? Let's try one more question and then we will move on to the infinite body problem. Yeah. There we go again. Quantum physics. No, quantum physics, F equals ma, just doesn't work that well anymore. Yeah. In fact, the idea about mass is, okay, you're tempting me with quantum physics. It's like, let's get out of the syllabus.
Does quantum physics work with relativity?
That's the one that they cannot reconcile. That's the problem. Out of the 4 fundamental forces of nature, the 3 fundamental forces, electrostatic, electromagnetic force, nuclear strong force, nuclear weak force, have been unified, meaning that they are able to come up with one equation that breaks into the 3 other forces in different scenarios. But the one that's the naughty one that refuses to reconcile is gravitational force. So the big and the small quantum physics just doesn't meet. Yeah, just refuses to meet. So that's why you never heard of this thing called relativistic quantum gravity. You have heard of it, but they have not developed a complete theory on it. Yeah. So in fact, there's this idea about quantum time. that time itself is nebulous, it hops around, that it is undefined. It's interesting stuff that people are thinking of. Yeah. Probably one of you will be able to unify that. Probably one of you. Probably. You never know. You never know. I'm a strong advocate. I think I told you this before. I'm a strong advocate that one day a constant must be named after an Asian. Or a unit of measurement must be named after not Chinese, why Chinese, but an Asian. Yeah, it can be a 4 barat or 5 yo or 6 hua. Yeah, 5 chews, 5 chews, 5 chews. Yeah, high chew. We need high chew. We need more chews. That sounds weird. No, I mean, you see, Newton, Tesla, Pascal, all these are names of people. Right. This sounds weird. Micro chews, nano chews. Okay, these two bodies over here, tell me, come on. You have to know what direction is it going to accelerate. Come on. Entertain me. If you don't know this, yes. This one. Agree? Yeah. Therefore, for this one, do you agree that 10 times g minus tension equals to 10a? And then this one, tension minus 5g equals to 5a. The trick is always to take the direction of acceleration as the positive. So in this case, I took downwards to be positive. That's why I take 10g, which is downwards, minus the upward force. For this one, I took upwards to be positive. That's why I took tension minus the downward force, which is 5g. The trick is always to take the direction of acceleration as positive. Okay? And then you can solve for t and g. Now the faster way was what Lauren mentioned just now. If you consider two bodies as one body, if you open up the two bodies like this, 10 kg and 5 kg, can you see that this is like a force pulling towards the right and this is like a force pulling towards the left? Can you see, if you open up like this. Therefore, the net force is, come on, 5g, yes, correct. So 5g force accelerates a total mass of 15, correct. So A equals to g upon 3. 2 steps, you can get the answer already. But like what I say, you cannot find tension in this method because tension, the two tension cancels out. So you cannot find the answer. You have to consider either this mass or that mass. Okay? Now I'm going to give you a problem that is an extension from this one. I'm going to give $5 to anyone who can come up with a convincing solution. Now to check whether you have derived it yourself or whether you actually copy it online, because it's quite a classic online question. I'm not going to tell you the name of the problem, otherwise you'll be able to find it quite easily.
Stop.
Same. A equals to G. Same. What's the acceleration of that mass over there?
All the big masses are the same.
All the mass, same. All this M. This is massless. The pulley themselves are massless. These are pulleys, by the way. These are pulleys. Yeah, these are pulleys. Weightless pulleys. Frictionless pulleys. Relax. This is not IB. This is, I must make it clear. It is not IB. Okay, Cine, this one, IB. Okay, I'm going to give another example. Just copy that question down and try it when you can't fall asleep. You try it, you might fall asleep. Or you might fall dead. It's like, heart attack. Too much tension. Oh my. In a row. Okay. When the lift is moving at a constant velocity, reading is equals to 60 kg. When lift is accelerating, reading equals to 45 kg. Right. I don't know whether you love physics so much that you actually put a weighing scale on the lift and then stand on a weighing scale and then start making measurements. But I've done that before. I've done that at the lift, the 40-story buildings over there. Yeah, you know, just across the road there's a 40-story building. Yeah, the 40-story HDB flat. A few of us, I gathered a few of us just. Actually, why not? Why not? But getting you out of school shouldn't be a problem because it's supervised, it's a small team. Probably one, yeah. We find a 1 hour 40-minute lesson, and then we start doing physics experiment at the HDB flat. Drop things from 40 stories. Oh, why not? Actually, that's a good idea. That's a good idea. Yeah, just make sure that we don't kill any residents though. Okay, so the reading of the scale when it's moving at constant velocity, 60 kg, and then it's 45 kg. Come on, common sense. Just your gut feel. Can you tell me what's the direction of acceleration? Down or up? By the way, please, there's only two ways the lift can accelerate. Some students can tell me left. Left. It's like, what? Yeah, it's like, the wire is like this. Tell me what direction does the current flow? Left or right? Up. Yeah. What? At least you die the wrong way now, right? You can tell me up, Sometimes the wire is this way. Yeah, into the river. Like, okay, up or down? Acceleration. Oh, you weigh less. Down or up? You feel lighter when the lift is accelerating down, right? Careful, huh? If it is accelerating down, must it move down? If it is accelerating down, it can mean two cases. It is getting faster and faster downwards, or it is traveling upwards and slowing down. How do you know the direction of acceleration? So, say for example, I got an object here, right? If I were to exert a force on this body which is traveling here, this will speed up. Agree? And since the force is in this direction, the acceleration must be down. Now let's imagine the second scenario. The velocity is going up, the force is this way, therefore the acceleration is this way. Does it speed up or slow down? Slow down, correct. So one of the common mistakes that students usually make is that when they think acceleration in one direction, the velocity must be the same direction. Not necessarily. Yeah, not necessarily. This is I think in TOK you might learn this. This is a thinking fallacy. That when one is zero, the other one overgeneralization basically. When one is zero, the others must be zero. One of the common mistakes made by students when they throw an object up and come down, the velocity over here is zero. What do you think is the most common mistake made by students? Acceleration is zero, correct. Which is not true. If acceleration is zero, then you should stay there forever. Then probably you're in a dream. Probably you're in a dream. Can? So this is a cognitive fallacy, tend to overgeneralize. So coming back to this, question number 1. Can you tell me what's the actual mass of the person? 45 or 60? 60, no tricks here. 60, yeah, 60. Why? This is a very interesting question that we need to understand. When you are traveling at constant velocity, what are the two forces acting on the person? Weight and normal contact force, right? So if the two forces are equal, because there's no acceleration, it's constant velocity, this must be equals to? Yes, correct. Which one does the scale read? This or this? This or this? You stand on the weighing scale, Mom, I'm measuring my normal contact force. Your mom will send you for a checkup. It's like, are you all right? Because your mom or your dad will be more used to saying that if you step on the weighing scale, I'm measuring my weight, correct? You never say, I'm measuring my normal contact force, but actually, if you think carefully, If the scale measures weight, does your weight change whether you're accelerating up or down? No. This is equals to m times g unless something drastic happens to the earth when you accelerate up or down, the g never change. Unless you lose weight, unless you lose mass for whatever reason, probably you vomit, your mass shouldn't change. So if you measure weight, the weight should never change. Therefore, by logic, since the value changes, it must have measured something else, which is your normal contact force. Can? Cannot? Cannot? Now, we'd like to give it a try and see whether you can find the value of the acceleration. I give you 2 minutes to struggle a bit, try to write an equation, just 2 minutes, 2 minutes. So if you have to struggle, you just have to struggle for 2 minutes. And I want you to go through that struggle.
Hey, sir.
Yep.
Can I ask you a question?
Sure.
About someone in a lift.
Sure.
So if you're standing in the lift is moving, so you move together with the lift.
Yes.
What if you jump and then while you're in mid-air, the lift starts to move down?
Okay, you're traveling at constant velocity, and then when you just hop, and then at the moment when you leave the flow, the lift accelerate down.
Yeah.
Then you're going to go up.
So.
Then you're going to go up. Yes, correct. And that's exactly what happens in circular motion. If you think carefully about this. Why is it that, I don't know whether you've been on those kind of fun rides in theme parks. You can actually stay over here. Right? And it goes like this. I don't know whether you've been into this kind of things before. Like you're in a cage and then the cage rotates vertical. Yeah? Actually, the first time I went for this kind of ride was in France. I don't know whether it's still there. The French Disneyland. You have a ride where you go into a cage and and then you can actually stand on the floor over here, not over here. Yeah, so why is it that you don't fall down? Because the cage is accelerating faster than g. If you think carefully, if you're on a lift and the lift accelerates down but lesser than g, you feel lighter. Am I right? But you won't fly. When you have the lift accelerating down at g, why? Because the cable snap. In Hollywood movies, it always happens. The cable snap, then the thing free falls. But actually in real life they don't, because most of the lift mechanism, they have a safety thing. There will be 4 grip that grips the lift to the bars beside. So it won't fall, but in Hollywood movie, it always does. So it will fall and then you'll start flying. Imagine if you were to accelerate downwards, say for example, you put a rocket booster, for whatever reason, what do you think will happen? Yes, correct. Exactly. So this is why in those kind of fun rides, you can actually stay on it because the cage is accelerating down faster than the acceleration of free fall. So you get to be up. Yeah. Yeah. So actually it's very interesting kind of roller coaster design. Probably one day, come on, don't go HDB. One day if you want to go for something big, go USS.
Yeah.
Go USS. Under the pretext of we're learning physics.
Yeah.
Not having fun. We're learning physics, yeah. Not having fun. It's not fun at all. It's not fun. It's all about learning physics.
The mummy ride has like the weightless.
Of course, the weightless, yeah. And then the GPE and KE conversion.
Reading like 6 times, right? So you can write 6 times.
You write 6 times, yeah. Okay, sure. And then the school is going to pay for it, best part of all.
Yeah.
Yes, of course. Ethan, can you pinch her face to see whether she's dreaming or what? Yes, you have a question.
If in that lift is accelerating at 2g.
2g's. Then you feel, if you close up the cage, you'll not be able to tell the difference, whether you're on Earth or whether you're on a roller coaster ride. Essentially. Say for example, at this moment, if you accelerate downwards at 2g, it means that to the person, he would feel a normal contact force because if you actually draw down the forces acting on him, it would be normal contact force and weight. So normal contact force plus W equals to m2g. So N will be equals to mg. So to the person, the N is what he experiences or she experiences. So to the person, he will think that he's in an environment where the G is G.